So number of poles in the sense number of phases. Come to the fifth one, operating mechanism. What is the operating mechanism for the breaker? Obviously, spring mechanism. Before there is a hydraulic mechanism is there. Now present or pneumatic is there, but present all the breakers are spring operated breakers. And if you see in the GIS application, they are having GIS, gas insulated switchgear. They are having SF6 gas, and that SF6 gas operating mechanism. Some manufacturers are providing spring. Some manufacturers are providing spring hydraulic. Means charging spring. It's charging through the spring when it is discharging. When it's charging hydraulic and when discharging the spring. So spring hydraulic mechanisms are there. But in AIS, air insulated substation, all are single spring mechanism only. So the next one is closing time and the opening time. So closing time, it's obvious it should be less than 120 milliseconds. So generally, we recommend 100 milliseconds. Less than 100 milliseconds is the closing time. Opening time should be less than 60 milliseconds. Less than 60 milliseconds. These are some standards of in IEEE, IS 13118. And these are the some practice. And come to the eighth one is the rated short circuit breaking current. The rated short circuit breaking current is nothing but our short circuit withstand current. How much current it has to break? So what is the maximum fault you are assuming that in your system? Obviously, 25 kV and 33 kV, 40 kV and 220 kV. So those will be a same here. The for 25 kV for 33 kV breaker and 40 kV for 220 kV breaker. Rated short circuit breaking capacity and withstand capacity also the same. Rated short circuit making current. So what is the making current? So there might be a chances that the breaker can be operated, can be closed in the fault. We don't know. There might be a chances the breaker can be closed on the fault. So at that instance also, the breaker should not damage. So it has to make the circuit. So generally that is, we generally consider that 2.5 times of the breaking current. Like suppose if it is a 25 kV for 33 kV, 2.5 into 25, 62.5. So 62.5 kV is the rated short circuit making current for the 33 kV breaker, and 2.5 into 40, 100 kV is the rated short circuit making current for 220 kV breaker. 2.5 we have to multiply with 2.5. Why the 2.5? So why we are multiplying with that 2.5 is generally we know the concept of that asymmetrical symmetrical faults. So generally when a fault occurs, the fault will be like this. And after that, it will enter into the steady state. It enters in steady state. So if you see that here, there is a no negative one. So this everything. So why it is this peak was occurred due to the DC component. Due to the DC component. This DC component is a ratio which depends upon the X by R ratio of the system. X by R ratio of the system times constant. So when the DC component exists, so obviously the fault will be this. So when a fault occurs, suppose when a fault occurred, this is sensing the relay sensing the fault here, and it will give the command to the breaker to operate. So the fault will be mostly comes up to this stage. So always the breaker will be operated at this stage of transient period. But the breaker might be close in the subtransient period, which is nearly 1.8 times of my 1.8 times of the transient one. So as a safety and the rule of thumb, they are using 2.5 times of the short circuit making current. So that is the concept behind this. So because always the breaker is operating here. to the fault detected by the relay and sending the command to the master trip relay giving the command to the breaker. So it's take time. So in that sense, the breaker, this wave, the DC component will not be there. So it will falls to come to here. So always the breaker is operating in this region, but there might be a chance that breaker might close in this region. So for this, we have to again consider that means we have to ensure that the breaker should be capable to withstand such a magnitude of current, which is nearly 2.5 times of the breaking current. So 2.5 into 25, it's 62.5 kA for 33 kV, 100 kA for 220 kV. And the first pole to clear factor, which is generally a ratio lies between 1.3 to 1.5. For 400 kV, you can see 1.5, and for 33 kV, you can see for 220 kV, you can see 1.3. So what is this? So it is a ratio that when a fault occurs, suppose RYB, if a fault occurred in the R phase, what is the voltage, the line to ground voltage of the faulty fault, the unhealthy phase to the voltage, line to ground voltage of the healthy phases. That is this. So it seems that when a fault occurred, the voltage, how much voltage it's rising up, it's nearly to 1.3 or 1.5. So that is a first pole to clear factor. It's not much needed. That is a parameter generally we will talk in the when we are discussing about the breaker. Next one is the rated operating sequence. What is the rated operating sequence is? So generally the breaker should be operated in some cycle. I mean that the breaker should be in IEEE it was mentioned that the breaker should be opened after 0.3 seconds. Sorry. The breaker can be closed and breaker again opened after 3 minutes. You can close the breaker. Again, the cycle repeats. It seems that is a duty cycle of the breaker team. I mean that you can operate the breaker in this cycle. Like you can open the breaker and in the next 0.3 seconds, you can close. Again, you can immediately open. And but if you open, then two times opening is happening. So the SF6 gas which is present in that, it is when it's opening, two arcs are forming. So SF6 gas which is present there get ionized. So it required some time to deionize or to again regain its strength of dielectric. So we required some time, that is nearly 3 minutes. Then you can again close the breaker. So this is the duty cycle of the breaker. So why I required this? Generally, this is the condition you can see in the auto-reclosure function. As I said, now we are having the three phases R, Y, B. Suppose a R phase got fault, a tree branch got hit on the R phase, and the fault was happened. It's a transient fault. So the breaker, by seeing this, the breaker is opening here, but it's checking that with some conditions that I will talk in the control and protection chapter. In the auto reclosure function was enabled, so that's taking some time, which is 0.3 seconds, and again I am forcefully closing the breaker. If a fault is, if it really is a transient fault, so okay, no issues. So it will run. If a fault occurs, suppose in the worst condition, if it is a permanent fault, it's not a transient fault, but I close it. So again, it has to open. Immediately it's opening. But due to this two times of opening, two shots of the breaker losing its dielectric strength, SF6 gas losing its dielectric strength. So it required again some time to regain its strength. So that was defined as 3 minutes across all the vendors as per IEEE. If you are not giving that, the energy cannot be handled by the breaker will blast. So that is the rated operating sequence. which is also called as a duty cycle. So this duty cycle is enabled if that breaker is having a future of auto reclosure. Auto reclosure in the sense individual pole operated. But if you see in a 33 kV, all are gang operated. So you cannot find the auto reclosure function in 33 kV levels because all are opening at a time. So for this, for that, the duty cycle will be from here. Close, open, 3 minutes, close, open. General. Yeah. So that's about the rated operating sequence. And come to the endurance class. This already we discussed in the isolator. Same. We are having a mechanical operation and an electrical operation. So in the mechanical operation, we are having classes of M1, M2, M3. M1, you can have 1,000 operations, M2, 10,000, M3, such M2, 5,000 and M3, 10,000 operations. Mechanical operations you can be you can have in that on that breaker. So it again depends upon the requirement, how frequently you are opening or closing the breakers. From your past historical data, you can see, oh, this is the number of operations generally I can see in my last projects. So I feel M2 is a better one for me compared to the M3 and M1. So it seems that. And similarly, electrical engineers class E1, E2, which is based on the how much current it can capable to break, short circuit withstand capacity. So these are the main parameters generally will specify. Suppose if I ask you that for us project, I will say I required a 33 kV 800 amps vacuum circuit breaker, 50 hedges, 50 hedges. The short circuit withstand capacity is 25 kA for 1 second. And this come to this making current 62.5 kA. And operating sequence 0 open 0.3 seconds. Oh, sorry, for 33 kV close open 3 minutes close open. That's enough. So there's a simple, a brief explanation, a brief description for your breaker. And one more important thing here. Always the breakers. In the breakers we are having two coils. One is a tripping coil. Other one is a closing coil. In the specification, we are again specifying some additional thing to those coils, like the coil should be designed in this way, and those are should be operated for 70% to 110% of the voltage. My closing coil should be operated for 80 to 120% of the voltage. So we are specifying something relay on this tripping coil and closing coil. We require 2 tripping coils in the breaker. So we have to specify all these things in the breaker technical specification, not here in the description in the bill of material or the bill of quantity for what you are preparing. Yes. So these are the main important parameters we have to look into.